In today's lesson, we are going to be looking at exponential equations and their applications. So to start off, I want to solve the following equations. Right? So in some cases, we may be given an equation, or an exponential equation. We might be given what it equals, and we want to solve to figure out what is the x value, or what is the variable, or what is the value of the variable. So this is this is similar to the standard form of our equation, right? Generally, if we think back quickly, our equation might be y equals ab to the power of x, and that would equal a certain value. So these equations that we're dealing with here and here are very similar to that. So similar to our equations, I want to try to get a common base. But first, these ones are a little bit different because we have additional values to work with. So because I'm multiplying 25 by 3 to the power of x, I want to cancel out this 25. So I'm going to divide both sides by 25. I get 3x is equal to then 675 divided by 25 equal to 27. And now because I have the 1 power by itself, I want to get it so that I have a common base. So we can write 3 to the power of 3 instead of 27. So in this case, now because I have common bases, therefore I can compare exponents. So x would equal 3, and I don't need to do any further solving. For b, 1.35 times 2 to the power of t over 3 equals 1382.4. Again, same idea. I want to divide this side by 1.35, divide the other side by 1.35. We get 2t divided by 3 is equal to 1024. Now our goal is to get a common base, right? So we already have 2 as 1, so let's see what we can get 2 to the power of to get 1024. If we work through a couple of them, maybe guess and check, we get that 2 to the power of 10 is equal to 1024. Now that we have common bases, we can compare exponents. So t divided by 3 equals 10. Because I'm dividing by 3, I'm going to multiply by 3 on both sides to cancel it out. I get t is equal to 30. So in some cases, we might have to solve the equation. And this might be an example of how we do that. So just taking in what we learned with the solving exponential equations with common bases. We're going to look at some specific scenarios in the exponential equations that we might deal with. Right, so Mike invests $1,500 into a fund that pays 6.5% interest compounded annually. The formula A equals 1,500 times 1 plus 0.065 to the power of t is used to calculate the future value of the investment. What will the value of his investment be after 10 years and 20 years? Right, so this is just an exponential formula or an exponential function. Right, we see that it's growing because it's 1 plus the percent. Right, and all we're doing in this case is just figuring, okay, if A equals, or the future amount is equal to 1,500 times 1 plus 0.065 to the power of t, but we know now that t is 10, what will the amount equal? So in this case, we're just plugging a value in and solving. So in this case, we get that after 10 years, the value is $2,815.71. Right, after 20 years, what would it be? Right, you might automatically assume, well, it's just going to double. That might not be the case, though, because of what it's growing by. Right, it's growing by 6.5%. It's exponential. Right, so if you look at an exponential function, it's not always consistent growth. It should be getting larger and larger and larger. But let's go through and solve. So we're going to take the same equation but raise it to the power of 20 now. And again, this is just a calculation. We should get $5,285.47. So after 20 years, $5,285.47. So again, this one was just about plugging the values in and calculating. A potato is placed in the oven at 300 degrees Celsius. The core temperature of the potato T after T minutes is given by the formula 300 minus T equals 208 times 0.96 T. What is the initial temperature of the potato, and what will be the core temperature after 3 minutes? So looking at this equation, right, it is kind of like an exponential function in what we've learned, right? We see at least this portion here looks like an exponential function, but this portion here is a little bit different. So in this case, because we want to figure out what the initial temperature is, we can't just look for this value, right? Because it doesn't make sense that the initial temperature of our potato is 280 degrees Celsius, right? That's a pretty hot potato, right? So it doesn't quite make sense, but initial temperature, that means the time is equal to 0. So let's go through and solve now. So 300 minus capital T for the temperature is equal to 280 times 0.96 to the power of T, which we know is 0. Anything to the power of 0 is 1, so this becomes 280 times 1, or just 280. And now to solve for T, we're going to minus 300 from both sides. We get negative T, because that minus doesn't disappear. Negative T equals negative 20. Divide by negative 1 to cancel out that negative in front. We get T is equal to 20. So therefore, the initial temperature is 20 degrees. Which makes more sense, right? That's more room temperature, right? So it makes sense that the original temperature of the potato is 20 degrees Celsius. The next part asks, what is the core temperature after 3 minutes? So we're going to do the same thing, except now we know that T is equal to 3, or the small t. So 300 minus T equals 280 times 0.96 to the power of 3. So 300 minus T is equal to 280 times 0.96 to the power of 3. This is just a calculation, and we get 247.73. We still want to solve for T, so now we're at the same steps as the last time. Minus 300 from both sides. We get negative T is equal to negative 52.27. Divide both sides by negative 1. And we get that the temperature is equal to 52.27. So therefore, after 3 minutes, the temperature is is 52.27 degrees Celsius. And so again, just the idea of plugging values in. You want to be careful though. Usually the initial value would be the A value that's attached to the bracket, but because we have a slightly different formula, right, it's not just our standard exponential function, we can't just say that 280 is our initial temperature. Next, a radioactive sample has an initial mass of 500 milligrams, or with an initial mass of 500 milligrams, has a half-life of 4 days. And half-life is the time it takes for a quantity to decrease to half of its original amount. So first we want to write an equation that models this exponential decay, where t is the time in days and A is the amount of the substance that remains. So for exponential decay, we're going to start off with A, and this is going to equal our initial amount, which is 500 milligrams, or micrograms, I think it's milligrams. So we're going to start off with, not 550, so we're going to start off with 50, so that's our initial amount. We're going to multiply it by our decay factor, and because we're losing half of it, our decay factor is going to be a half. The reason I know it's a half because we're talking about a half-life. Right? So we're losing half the amount every time. Now, the cycle or the length of a half-life is 4 days. So that means every 4 days it decreases by a half. So normally in our equations, we would just say something like this. Right? And we'd say that t equals days. However, this equation would mean that every day we're losing half, when that's not the case, because it's every 4 days that we lose half. So I need to make the exponent a fraction. T over 4 will equal is our exponent. So for example, this means that if I were to plug 4 in, that is 1 half-life. So after 4 days, I should lose half. Right? It would become 50 times 1 over 2 to the power of 4 over 4, or just 1, or 50 times a half. So that would work out. So when we're dealing with half-life, our exponent should be a fraction. The denominator will be the length of the half-life. Right, so if we need to put that in here, length of half-life. Here we have our initial amount. And here it's half for half-life. What is the remaining amount of radioactive material remaining in the sample after 10 days? So here it's going to do the same thing, except we're going to decrease it or have our t equal to 10. So we're going to take our formula, A equals 50 times 1/2 raised to the power of 10 over 4. So here, this just becomes a calculation. 50 times 0.5, or half, raised to the power of 10 divided by 4. We get 8.83. So 8.8 or 8.84 milligrams is what is remaining. So all this is just a calculation, so just make sure you are comfortable doing this on your calculator. If you want to rewrite it, you could say A equals 50 times 0.5 raised to the power, and then 10 divided by 4 is 2.5, and do the calculation that way, and you still get the same answer. Right? So just rewritten without the fractions. C asks, how long will it take for the radioactive sample to decay to 6.25 milligrams? So here, this is telling us what our A value is, what our remaining amount is. So I'm going to take my equation. So 50 times a half raised to the power of t over 4. I know now that A is 6.25 equals 50 times 1/2 to the power of t over 4. And I want to solve now. I want to solve this exponential equation. So in order to do that, similar to what we did in the warm-up or at the very beginning, I'm going to divide both sides by 50 to cancel out the 50. I get 1 over 2 raised to the power of t over 4. 6.25 divided by 50 gives me 1 over 8. Because it's 1 over 8, now I need to try to find a common base. Right? I can convert the 1 1 over 8 as an exponent of 2 to the power of -3. And I can do the same thing with 2, or 1 over 2. I can rewrite that as a power of 2 to the power of -1 to the power of t over 4. I can simplify this a bit. And now, because I have common bases, I can compare exponents. So -3 is equal to -t over 4. So I can bring the 4 up, or I can multiply both sides by 4. I get -12 is equal to -t. I can divide both sides now by -t, or sorry, -1. And I get 12 equals t. So therefore, this is our final answer. So therefore, it will take 12 days to decay to 6.25 milligrams. Right? So just about why or how we can solve the actual equation or exponential equation in certain scenarios to find our value. Right, so all of this is just looking at different scenarios that you might come across, different types of questions. Either you're solving the exponential function, or you're coming up with the exponential function, or you are plugging values into our exponential function and solving, right? So all different scenarios that you may come across that you'll be expected to know.